We're still talking about the gradient. And now we talk about the third interpretation or use of the gradient, which is a way to generate a vector field from a potential function. And this video will explain what those terms mean. Here would be a vector field. This big F is a vector, a function of x, y, and z coordinates, where each coordinate itself is a function of x, y, and z coordinates. This means for every point in three-dimensional space, or potentially three-dimensional space, there's a vector associated with it. Think of, say, water flowing through a pipe, a big pipe. Inside that pipe, each point in space inside that pipe, there might be a vector that represents the direction and strength and speed of flow of that water. It might be turbulent, it might be faster through the middle, etc. At each location inside the pipe, there's a vector that describes flow of water at that particular point. You could start generating a simple one in this simple case, just a two-dimensional case. Say here's the vector field. Let's start examining some points. Let's say the point 1, 0. Where x is 1, y is 0. So this goes away, x is 1, I just get j. Here's the vector. See this vector? That's the vector associated with this point. At that point, I have x is 1, y is 1. So I'll be going up 1 in j, to the left 1 in the x direction, and the magnitude will be the square root of 2. I get this vector. And up here where x equals 0, y equals 2, I get minus 2 in the left direction. Keep doing that for a bunch of points, and you can start drawing something that looks like a vector. Here you get sort of intuitive feel. It's sort of this swirly thing. It's bigger the further out you get. It shrinks as you get close. Always in this sort of circular direction. But anyway, that's the idea and sort of intuitive feel for a vector field. If some function phi is differentiable, its gradient produces a vector field, or its gradient is a vector field, right? A gradient is a vector, and it came from taking the gradient of a scalar function. So gradient is a way to generate a vector field of a differentiable scalar function. And when that happens, you call that vector field conservative. Any vector field that can be generated from a potential function by taking its gradient is conservative. You can have a vector field that doesn't have such a potential function. Those vector fields are called not conservative. That's the definition of conservative, which we'll be using later in the course. So here's a simple scalar function phi, x, y, and z. Take its gradient, I just get yz, xz, xy. That is a vector field. And it's a conservative vector field because it came from a potential. By the way, you're gonna be seeing P, Q, and R a lot in the future of this course, where P just means the x, y, and z function describing the x component, Q is the y component, R is the z component. This vector field, this is a vector field. You get a vector for every x, y, and z. It looks kind of similar to this guy, just in general format. But trust me, it can't be generated from any scalar function phi. It doesn't have a from a potential function. It has no potential function, so it's not conservative. How about another example? Two-dimensional gravitational field. Some constant over this radius. Let's see what a graph of that looks like. Let's see, when x and y are both 0, here, I get like minus infinity. Right at the origin, value of u is, it approaches negative infinity. As x and y get large, that means this radius from the center gets large, u gets small. Approaches as x and y get large, this thing approaches. You get this funnel type thing. What's its gradient? We'll start taking this guy's partial derivatives, and we'll go through that. Here's its partial with respect to x, partial with respect to y. It simplifies a bit. And I could take out the common terms, and I'm just left with the vector xy. Part out front just scales that direction vector. And if its direction is x, y, that means it's on a line through the origin. So we just showed that. And what's this look like? Well, it's always on a line through the origin. And actually what I drew here was minus this, because that would be the direction of gravitational force. When I do minus this, they'll point towards the origin, and they get bigger the closer you are to the origin. As x and y approaches 0, because it's raised to a negative component, I get bigger and bigger numbers. So it's really big. And you can kind of see that. The slope of this thing kind of gets really big the more inward you go with it. Anyway, those are the three interpretations. It took me 3 videos of the gradient. Steepest ascent, the direction of steepest descent. Its magnitude is the rate of that ascent. Normal to a curve or surface, which means it's perpendicular to a curve or surface. Second interpretation. And the third interpretation is a way to generate a conservative vector field. That concludes the gradient.